Welcome back to Quick Chemistry. If you're unfamiliar with what the structure of an atom is, or what it means to calculate atomic mass, check out my video on atomic structure and mass before coming back to this one. In previous videos, we've established that elements are defined by the number of protons in their nucleus. All atoms of the same element have the same number of protons. I've also mentioned that atoms of the same element can have varying numbers of neutrons in the nucleus, giving different atoms of the same element different atomic masses. Species of an element with varying numbers of neutrons are called isotopes, which is what we're going to talk about today. Isotopes are atoms of the same element, and so have the same number of protons, but have varying numbers of neutrons. Each additional neutron doesn't change what element the atom is, but adds to the atom's mass, resulting in any given atom of an element having a potential range of atomic masses. When we consider the relative abundances of these isotopes, and use these to find the weighted average of these masses, we get an element's relative atomic mass, sometimes referred to as its atomic weight. This is why, despite getting whole numbers for individual atoms' atomic mass, the periodic table gives decimal values for the relative atomic mass of a species. It's an abundance-weighted average. The equation I have here on the screen is what we use to find an element's relative atomic mass, AR. Firstly, we take the atomic mass of each isotope and multiply it by its abundance. We then add all of these values together to get the relative atomic mass of the species we're examining. It's that simple. Let's look at the two naturally occurring isotopes of lithium, lithium-6 and lithium-7, in order to determine the relative atomic mass of lithium. Note that the 6 and 7 in lithium-6 and 7 refer to the respective atomic masses of these isotopes. Lithium-6 has an abundance of approximately 7.5%, and lithium-7 has an abundance of approximately 92.5%. If we substitute these values into our equation, we get 6 times 0.075 plus 7 times 0.925. Note that I've converted the percentage abundances into decimals in this calculation, but you can also represent them as fractions or as a percentage. I personally prefer using decimal representations because I find it far easier to put into a calculator. When we put this into a calculator, we get a relative atomic mass of 6.925, which can be rounded to 6.93. This is incredibly close to the literature value of 6.94. The reason for this difference is because the literature value considers isotopes of lithium which I haven't, including lithiums 3 to 5 and 8 to 13. I chose to only include lithiums 6 and 7 in my calculations to keep things simple, and because they're the only stable isotopes of lithium. A stable isotope is one which will not spontaneously undergo radioactive decay, or do and have half-lives which are too long for us to measure. This is in contrast to unstable isotopes, which will undergo spontaneous radioactive decay. Keep an eye out for future videos on radioactivity and radioactive decay for more on this. And that's it for this video. Be sure to like, subscribe, and comment down below with further topics you'd like me to cover. Until next time.